So, we are now going to have 3 hours. 3 hours is too much to make to give it in one session, so we'll have an hour and a quarter, then 15 minutes break, then another hour, and that's the plan for today. And what I want to accomplish today is to finish the treatment of tight binding, show that we get the same qualitative results as the nearly free electron model, and then present tight binding in a totally different way, which is somewhat already more connected to what people are doing in quantum field theories, not full-fledged quantum field theory, but still it has some of the ingredients, and that's a different way to see this tight binding model. And it also actually helps very much to explain how one implements tight binding model in a quantum computer, in a regular computer, even numerical methods of calculating properties of solids. Okay, so where were we in the last time? We said that we start from a tight binding model. Said that we start from an atomic model which we know the solutions. We describe the full Hamiltonian as the atomic model plus delta U, and delta U is a contribution of all other atoms in the lattice. And we want to write down the total wave function, which will correspond to the Bloch theorem. And therefore, psi r plus a lattice vector total wave function of the system, and we can see that this fulfills the Bloch theorem by writing the following. What did I do here? I just multiplied here by ik dot r and divided it by minus ik, or multiply it by minus ik. But if I replace here r prime let's say r prime minus r, so all that's written here is actually equal to what's written here. Question?
What's the meaning of the r prime?
Has no meaning, just a summation. It's a mute index. So I always can replace it by something else because it goes over infinity. It has no boundaries. Exactly, it's just the same thing. Well, actually, it's back to Bloch theorem. It's just restating Bloch theorem. Okay, so that's very nice, but we're still have the task of solving the full Hamiltonian. So, that's just the Schrödinger equations that we want to solve. And K is just an index of some eigenvector and eigenvalue active. Okay, so I'm looking at this equation and asking myself, what happens if I multiply it by an integral over another eigenvalue of this equation? Okay, so let's explicitly write what appears here. So I have Haven't yet done anything. Just wrote down. Okay, let's look at the first term. Okay? Oh, didn't do anything, just copied it. But what is important about a Hamiltonian? What is a property of an operator that's a Hamiltonian? Right, hermetic. So I don't need to write here the same Hamiltonian. The fact that I moved it doesn't change anything. And this guy, I know what's the solution. This is the atomic eigenvalue. Okay, let's go and see what happens. I want to rewrite now this these terms. So I just rearranged the different parts of the equation. Okay, and basically in order to make some progress, I have to say something about psi, the general solution of the equation. What do I know? Basically, I know that this solution fulfills the Bloch theorem. And here I can have any solution which is has a repetitive behavior, but I will use, according to the logic that I've used before, the combination of the atomic solutions. Now you may ask me, why didn't you just simply write here psi n? According with the logics that we did before. Right? Could just write psi n. Why do I write here a linear combination? Well, first of all, because I can. I'm not limited only to one of them. I can write here any linear combinations. And sometimes in some solutions it helps, although for what we will do here in the following steps it won't make any difference. But I'm just mentioning it, so if you want to go a bit deeper into tight binding model, you understand that it doesn't have to be necessarily the atomic wave function. It can be a linear combination of them. But as I said, for our purpose, at the moment, it really doesn't make much of a difference. I'm going back to this equation. Just writing it down. And I wrote here phi instead of psi n, just to make this point that I can have a linear combination. Okay, it may look a bit pedantic, but if some of you during his or her graduate studies will go into a bit more advanced solid state, this is called Vanier functions. Again, we're not doing anything with it now, but just so the ground work for understanding what is done there would be existing. Okay, so I'm rewriting everything and inserting phi in the Hamiltonian. What did I do here? Nothing. Just substituted psi by this. So what did I actually do here? This
Take the first. You take the first.
I took the first term, r equals 0, wrote it separately, and all the rest. Trivial and looks just long and a bit strange, but it has a real good reason. Why is it? What actually is the most basic property of an atomic wave function? But that's correct for any wave function. I'm specifically talking about an atomic wave function, as let's say compared to a free electron or anything like that. Well, atomic wave functions are usually for electrons. They are fermions, they are antisymmetric, but that's not the point. Something much more basic. Okay, let's step one step behind. What's different between an electron on an atom and a free electron? No. A free electron is everywhere. An electron on an atom is close to the nucleus, right? It dies off exponentially. So it's a very localized wave function that dies off exponentially. So the main contributions of these integrals comes from psi that has the same r. Why? These guys, you have one center at one point on the lattice and another electron around another atom in the lattice, right? That's the difference between r minus r and r. So when I'm multiplying two exponential functions that are far from each other, what is the result that I get? Small, almost zero. Why am I saying small and not zero? Because if I throw all this, I'm back to an atomic model and I don't see the whole lattice. But what will I do here? What is the perturbation? I'll say that if I have two electrons, that one is on an electron and one is on an atom and one is on a nearby atom, it has some contribution. But two electrons that are far away, then it's zero. That's the perturbations that I do. So I won't retain here all the r's. I'll keep it to a finite number of r's, usually just nearest neighbors. Okay, so instead of summation here on an infinite number, I'll have a summation here on a very small number of close-by atoms. If you want to think about it from a physics point, if I have two atoms that are close to each other, I still can have tunneling between them. But if they're very far, no, I won't have any tunnel. You can say, no, sorry, it has still an exponentially small probability, but it's still exponentially small even compared to the tunneling between close by atoms. So at one point I can neglect it in any perturbation theory. So that's exactly what I'll do. And another things that I'll do here, and sorry, this should be M. What happens when I multiply two wave functions that are not on the same level? Two atomic wave functions that have a different quantum number. Excuse me?
It's not it's not like this, it go to zero.
If R here would have been equal to 0, so they are orthogonal, right?
Yes.
By definition. But they are here on two different atoms. Nevertheless, it would be very small. The same type of argument is here. Because I'm multiplying it by some function here, the integral is not necessarily 0, but since there are different levels and this is a small contribution, I could assume that they are quite small. So first of all, the first approximation that I'll do here, I'll get rid from the summation over different m's and say I'm looking only over one level. Questions? Let's look on this on should have screen domain because these are ends. N. Okay. Teoria nestabilna. Okay, someone says that I missed something else here. Hopefully not. Okay, so I'm claiming that I can choose just n equal n. Okay? Why? Because if there are two different levels, if I had here no potential, what would be the result? 0, by orthogonality of atomic wave functions. The fact that I have here a small potential, it can be non-zero, but it would be very small. Same here, even stronger here, because I'm on two different locations. Here it's not necessarily 0 because the claim is only that it's equals 0 for large R equals 0, because then it's just orthogonality. But even if they're removed, it's clearly very small. Okay, so I can choose a specific n, and for simplicity, I'll just call it 0. What's a 0? Any atomic level that I choose. Doesn't matter. So I'll rewrite Okay, so I decided n equal m, and instead of I'm choosing a specific m, so I call it 0 and just replace everything. Okay, what's good with that? First of all, out of the game. That's what I told you at the beginning, that we're writing it as a linear combination, but for us it doesn't matter. Okay, now I'll use the fact that the further out the two wave functions are, the smaller is the result. So I don't have to sum over all these r's. I'll put a cutoff at some distance, because two exponential functions that are further out, the smaller they become, the multiplication. And now, just as a convention, this is an integral. It depends on the form of the fact of the potential and what is the atomic wave functions. But after the integration, it's some number. So we call it beta. write here an integral. After integration, on what does this integral depend? Only on R. Only on big R, correct. So I'll call it alpha of R. Same here. Some form, call it gamma of R. So I can now rewrite the result for EK. We're almost there. Just because in the integration it doesn't matter if you change here the integration factor to R plus R. And also from symmetry, I don't care if I'm calculating the wave function between this atom and this atom or this atom and this atom. They're equal. Okay, so what did I do here? Okay, this I just copied. Here I copied this guy, and I made here, of course, a minus. And if I assume that this is a small correction, I'll get here 1 times whatever appears here, and it's a small corrections times a small corrections, and I can't forget about it. Okay, and what's A instead of R? Nearest neighbors. Instead of summation over all the R's, I'm taking just the nearest neighbors. Okay, now let me be a bit more specific and think about simple case of a simple cubic lattice. Okay, in a simple cubic, how many nearest neighbors do I have at a distance A? For 2 dimension 4, for 3 dimension 6. 6. For 1 dimension 2. For D dimension 2 times D. Okay, so let me write the term specifically. So we are discussing a simple cubic. Okay, I just wrote the summation over the nearest neighbors. I will stop writing here alpha because all of them are alpha, no point. Okay, ik plus e, the minus ik is just twice cosine. And now we finally can talk about what does this tight binding approximation tell us. We started here at the end of the day with a single atomic level, E0, right? That was our initial. Ended up with some shift of it by an amount of B. And we got here many levels depending on Kx, Ky, Kz, which the largest of it is 6 gamma and the smallest is minus 6 gamma because cosine goes between 1 and minus 1. That's our band. Gamma depends on just the properties of the atomic wave function and could be different for each level. The number here 6 comes out of the number of nearest neighbor and can be different for different dimensionalities and different lattices. Let's say if it would have been a square lattice in 2 dimensions, we would have here between 4 gamma and minus. If it would have been it would have been a one-dimensional system, it would be have been between 2 gamma and minus 2 gamma. So, to sum up the solution, we start with an atomic potential which has several levels, which I number here E0, E1, E2, and so on and so forth. And after performing the tight binding procedure, I end up with levels that are a bit shifted and broadened. In this case, and so on and so forth. These are the bands. These are the gaps. At the end of the day, the same picture as a nearly free electron, where we started from a totally different starting point. What happens, let's say, in a case, the values of B and gamma depends on the particular forms of the atomic wave functions for the given levels. Now you can tell me what happens in a case, let's say that here I go, well, I'll use a different color here. Okay, where the level shift plus the broadening goes into the lower band. Can happen. It's a situation. So then the effective band will be much wider with no gap between those two levels. Is that what makes properties of materials interesting? Because for different lattices, for different atoms, you can have such situations, and it describes the properties of this particular material. It's not impossible. It can happen that a gap is filled and we have a much wider band. Okay, now you can come and ask me, you started from the point of view that nearly free electrons are similar to tight binding models. That's what you sell us all the last lecture. This is the energy here. For a free electron, we know what is the energy. Right? This is not similar to that. Perhaps in both models you have bands, but they're very different from each other. The dispersion relation is completely different. So the answer is not really. Let's look on this term. 0 minus B, and for simplicity I'll write here for the 1D case, as I've written here basically. Okay, I didn't write here kx squared, ky squared, kz squared. Okay, so it's minus 2 gamma cosine Ka, right? Let me look what happens at the edge of the band for very small values of K. For very small values of K, or I'll be more specific, for K much smaller than A, so then 1 over A, sorry, for K much larger than 1 over A. Long wavelengths, small energies, right? It's much smaller. Right, becomes Ka much smaller than 1, K much smaller than 1 over K. Okay? So I can expand the cosine in a Taylor expansion. Okay, when the argument of cosine is 0, the cosine is 1. I move a bit from 0, I get something smaller than 1. Okay. This point is just the lowest energy in the band. The dispersion relation is just k squared. Exactly the same as we have gotten from the free electron model. An even more interesting idea. If I say that gamma alpha squared is equal where m star has a name an effective mass. If I look on the spectrum of these electrons in the lower part of the band, they behave as a free electron with one small difference, that its mass is not the electron mass as we know from particle physics, but is given by so we have a particle that has a charge of a mass, behaves as a free particle as long as I don't go to too high k's, but its mass is different than the electron mass. So perhaps that's the first time that you encounter a concept in physics that comes out an emergent particle. Basically, we have here a particle that behaves like a free fermion. It has a charge of an electron, but if I look on its spectrum and its kinetic behavior, it behaves like a particle with a different mass. I don't know if any one of you ran into in popular science in the term heavy fermion system or heavy fermion metal. You can have situations where lattice structures have electrons with effective masses that are 100 times more than a regular electron. Which means that for things like conductance and things like that, if you remember our Grude equation from the beginning of our treatment of electrons, behaves as if a particle that has a much larger mass. if I'm going to the upper part of the band, close to the other edge, so I'll develop Ka not around 0, but around pi. I'll have the same description, but with a minus. And there I have a system that behaves as if I have a positive charge electron with an effective mass, or a positron, or holes, it's sometimes called. So we see that the interplay between the lattice and the electrons ends up in something that looks to us as if another particle is playing parts there. And now this has very deep implications for physics, because when we are measuring something on some scale, we might see a behavior that is very different than the constituents of this system. I have an emergent behavior that to me looks like a particle with other properties. And this is a theme that comes back in physics in very different topics. But here we meet it in condensed matter physics. Unfortunately, I don't have the time in this course to do it. But let's say a two-dimensional free electrons on a lattice that you put a magnetic field, you can see there a behavior of a particles that is neither a fermion or a boson, but something that is different between them. Or if you want to think the wave function of a fermion is antisymmetric multiplied by minus, but in boson it's multiplied by plus, and here it's and in this case it's multiplied by a phase. And it's not a particle, it's not a, but if you are measuring the properties of the system, it behaves as if it's an axion, particle that is neither a fermion or a boson. Okay, I think this is a good point to take a break. When we return, we'll go through this game as basically a very similar idea with somewhat different mathematics, and basically it will tell us also something about what happens when we are looking on a discrete space, like in computer simulations. That has endpoints. I'm drawing it in one dimension just to keep it visually simple. It can be done in 2, 3, or whatever number of dimensions you want. Let's assume that each lattice point could be in one of two possibilities. Either we have there an electron, or we don't have there an electron. What happens if I have more than one electron on a point? Can't be done. These are fermions. And we forget spin for a moment. Okay. So how can I describe such a Hamiltonian? and I'm limiting myself to the single electron descriptions, that I have only one electron in this lattice, although you will see almost immediately at least what is a path to generalize it for more than a single electron. And that's what you will do in advanced quantum mechanics, many particle physics. Okay, so let's assume we have one electron here in the system. I could do the following thing. I can create an electron on site I. You are familiar with this language from the harmonic oscillator. And I can annihilate an electron on site I. These are the only two operators that I can essentially use, these and a combination of them. From your experience in harmonic oscillator, what is this operator? Number of electrons on site I. Because if there's nothing there, you can't annihilate. If there is one there, you annihilate it and recreate it, and you counted one. If I'm trying to annihilate twice an electron on the site, the maximum, because these are fermions, can be 1, and if I try to annihilate twice, it's 0. Same way if I'm trying to create something twice. If these would have been bosons, the rules would have been different. But since it's fermions, it's very simple. You can either have an electron there, one electron, or no electrons. So, what is my Hilbert space? Okay, just should have begun. This is material that doesn't appear in Ashcroft. Until here, what we did is chapter 10 in Ashcroft. The material that I'm giving now doesn't appear in Ashcroft. This is a more modern representation of the material. Okay, what is a Hilbert space? We said we are still doing only single electron physics, and therefore this is a state on the lattice. Why is this a state on the lattice? Tells me on site 1 I have 0 electrons, on site 2 I have 1, on 3 till n I have no electrons. Let's say C2 on this state would have given me while what will this give me? 0, because there's no electron. Okay, from these building blocks, I can easily write a tight binding Hamiltonian, just will give the description that we obtained previously, and it goes the following. The operator if there is an electron in any one of these sites, it gives me an energy E0. If there's nothing, it gives me nothing. And okay, what does this term do? And the gamma is the same gamma that we had there. So let me take an example of the state that we used before. Okay, I annihilate on site 2, create on site 3, okay, just moved it. Why do I have here a term and its opposite? Because the same that I can go to the right, I can go to the left. So I have to write down the two options. That's the physical explanation. The mathematical explanation, this guy by itself is not Hermitian. If I take down here dagger, which is not equal to this term. So this term is not Hermitian, but the combination of both, this one will give me this one, and this one will give me this one, and the summation of both are Hermitian. So just the symmetry of going left or going right is also expressed by the hermicity of the operator. So I need both terms. Good. So how do I solve this Hamiltonian? Well, how did I solve anything for a lattice? At this stage of the course, you saw an example for it in Bragg scattering. You saw an example of it in phonons. You saw an example of it in Bloch theorem. Fourier transform. No, Fourier transform. Everything that has translational structures, translational symmetry, you approach it with Fourier transform. Okay, and here, without going into the exact mathematical definition, but I'll be bold and do a Fourier transform of the creation and annihilation operators. They'll claim
May I ask a question?
yes, but let me just write it down and then ask you a question. Please.
For the Hamiltonian, the second term, why there is a minus in front of the interaction energy?
Why it's minus?
Yeah.
Okay, that's a great question. Okay, let's assume that it's plus. If it will be plus, it means that movement of the electron costs energy. Therefore, an electron will never spread out. And the ground state solution is, I put an electron at a position, it will stay there forever. And that we know is not the description of a free electron or the solutions which we saw previously. Actually, it's interesting that the perturbation theory in tight binding gave us a minus wizard that we'll have to insert. I'll show you also a different way to get the minus here from a direct discretization of the Hamiltonian, which will give you also a behavior that is very similar to it, but let's wait for it. In the meantime, I chose minus because of this physical conditions that I want if I put an electron in a point, it won't stay there. So I'm looking on this, and then you can come and scream on me. From where did you bring this strange structure? But look on it. What do I have here at the end of the day? All I have here is a scalar times a creation operator. And a lot of terms of it, n terms. Sure, I'm allowed to write it down. In a moment we'll see why it's useful, but no problem defining. So if I would come to you and say I want to write an operator C1 plus C2 1 over root of 2, why not? It's an operator like any other operator. So that's also some constant times an operator, sum over a bunch of operators. I'm allowed. Why does it help? That we'll see in a moment. Of course, okay, here I should have defined K. K I need from the cyclic boundary condition. And as we are sorry, let me just write here N, not to get confused with the I here. Okay, let me transform Fourier. You go over all the nx's. First Brillouenzo. That's the whole. Okay, so I want to write here the Fourier transform of the Hamiltonian operator. Just copy what appears here. Just changed from I to N, just not to confuse with the imaginary number I here. to get confused with I again, so I'll use J. Okay, let me treat first the first term. This is the first term of the Hamiltonian. Okay? Yes. Okay, I have here three summations. Can change the order. Okay? Just change the order of summation. For a finite sum, I always am allowed to do it. And of course, you can scream on me that I forgot the 1 over square root of n and 1 over square root of n, so I have here 1 over n. What is the result of this summation? This is perhaps the most important summation that you'll use as a physicist. Kroneker's delta, delta k, k prime. If k is equal k prime, it's n, and it's killed by 1 over n here. If it's anything else, it's 0. K is not equal k prime. And if you have one mathematical summation that you should take out of undergraduate studies in physics, it's this fact. Okay, so after Fourier transform, we return to a form that is very similar. Here it was E0 times Ci dagger Ci. Here it has a very similar structure. Okay. What happens? to the second term. Okay. What was the second term? Second term was okay. Same game. We'll replace them by BKs instead of CIs. CNs. J's just not to be confused. Okay. So this is the first term. All that changed because I have here a j plus 1. I have in the phase also j plus 1. Plus E. That is the opposite. Minus I k a j I k a j plus 1 bk all I did is replaced C by B according to our definitions. Okay, same game, changing order of summation. Pulled out everything that doesn't depend on J outside and left everything that depends on J here. Here, the part times 1 doesn't depend on J, so I can put it before the part here of plus 1 doesn't depend, it's only on plus and minus. Both of them are multiplied by k prime. And inside I have the same multiplication. This is our good old friend, the Kronecker delta. And we get okay. Now, what is the solution to this Hamiltonian? Clearly, it's diagonal in the k states, and the energy is just E0 minus 2 gamma cosine Ka. So this gives us a very easy visualization of the tight binding model. All it says that I have energy of being on a site, and I gain energy by hopping to the nearby site, and that's the whole physics. Nothing more. And we got it extremely, extremely simple. Now, why did I say that it's connected with numerical solution of Schrödinger equations? Okay, let's look into it. Oh, basically I solved it and saw that if I'm in a K state, the energy, this is the number of electrons in a K state, right? And it's just this term, which is 2 cosinus K, plus E0, which is the energy that we got from the perturbation. Right? Mm-hmm. And now my claim is, actually, you know it from simple Schrödinger equation. Let's say I want to solve Schrödinger equation on a computer. Okay. How would I approach it? Okay, you're jumping a bit too forward. First thing, I have to somehow represent psi x on my computer, right? I have a problem. Computers, or at least digital computers, are discrete entities. All data is represented on a discrete set of variables, while this is a continuum. So what do? You say, okay, I'll take my continuum, and instead of keeping a value at each value of x, which I can't because it's infinite, I'll break it up to chunks of size A, and for each such chunk, I'll keep a value of psi there. So what did I do? Basically, I went from psi of x to psi of I. Well, I'll use here j again, not. Right? And I have here a point j equal 1, j equal 2, and so on and so forth. Okay, so I have basically a vector with n numbers which represent the value of the wave function on each point. So actually, just by the mere fact that I'm dealing with a digital computer, it forced me to introduce a lattice. I can't describe space by a continuous variable. I have to represent it by a lattice. Although from my point of view, I don't care about this lattice. I don't want it there at all. I'm forced to introduce it just because I have finite memory and I have to deal with a discrete entity. Okay. Here I have a differential equation. Okay, again, this is a continuous operator. Computers don't deal with continuous operators. So you say, okay, let me try to discretize it. So, dou x dou of psi at some point I. Because I have my wave function only as a set of numbers. How do I describe it? Well, how about this description? Okay, you can claim yi minus I minus 1. You could choose I plus 1 minus I or something else. Okay, I'll compensate in the next stage. Yes, that's the second derivative. the first derivative minus the nearby first derivative divided by a. Okay. The right hand side is simple. So I have here
It's a plus 5i.
minus plus. Correct. Okay, and for each I, you have that equation. Let me write it down in the matrix. Of course. And this is the term along the diagonal. Right, 4. Why? Because let's choose some point here, psi 2. I don't want. So psi 2 has psi 2 is E plus this term minus the value of the one above it and below it. So these are the two diagonal terms that are by the main diagonal. So just by discretization of the Schrödinger equation, we got the nearest neighbor tight binding model. That's all that came into the game, because what do? You're either on the site or you hop off the site. Nothing more, nothing less. You hop to the right, you hop to the left, and that's that. Solve this equation and the eigenvalues will be exactly the eigenvalues that we got. Just gamma here is minus h squared over 2ma squared. And the energies are E, same as E0. Here we got a B, a beta, if you remember, and that's that. So any type of discretization of space, actually, if you write down the discretization, you get tight binding model. And therefore, tight binding model is also used in quantum simulation. It's classical computer simulation of quantum systems. Just because if you're getting here, all you have to do is write down some kind of matrix, diagonalize it on your computer, and get the solutions, the eigenvalues and the eigenvectors. And basically, you got here tight binding without knowing what is tight binding, just by discretization. And why? Because the physics is the same. When you do discretization, you introduce a lattice. So now you can come and say, okay, but we know that the spectrum of a lattice in tight binding is different than a free electron spectrum. Right? It's a cosine. It's similar to a free electron, only at some limit, at k, a much smaller than 1. But that makes complete sense. You introduced here discretization to the system not because there was a real physical discretization. It's just that your computer couldn't handle continuum. So, when you are doing this discretization, what do you say to yourself? Well, it will catch the physics on long length scale, but it can't give you the correct physics at scales of A, just because that's discretizations that you put by hand. You want to get a better estimation for shorter scales? Make A smaller, take more values of your vector. But as long as K is much smaller than 1 over A, or the inverse of it is much larger than A, you got a completely good description of the system. So, although tight binding seems very far from a numerical solution of the wave functions of a free energy, it comes back. What do you do if you have here some potential? Write in a potential. That's a way to solve any of the problems that you ran into in at least the first semester of quantum mechanics. Just use this thing, write down a matrix, diagonalize it, and you solved it. And for a typical PC nowadays, diagonalizing a 1000 by 1000 matrix, which is usually for 1D problems a good size, will give you quite accurate solutions of the problem. So you can't put any problem of a wave function of any in a one-dimensional box in any type of potentials that you want, and it shouldn't. It's no problems to pull it out. So the question is from where A comes into the game. A gives you the... Now think about it. You are going at the end of the day and looking on large Ks. So see what happens for large K, and you should eliminate A out of the game. Okay, so I'll just do a very short preview on what we are going to do in the next lecture on Sunday. We're going to treat semiconductors. Why? Because semiconductors, as I said, is the basic of much, if not all, of the current technology. Okay, what are semiconductors? Semiconductors are materials where we have a gap, and at zero temperatures they're insulators. So what's special about semiconductors? The gap is small. Small compared to what? No. So we have a conductance band. We have a valence band. And we have a gap. And let's call the size of the gap Eg. The typical energy scale under which all of us live is the room temperature. So around 300 Kelvin. What is the energy available to any material in room temperature? kBT. We don't have anything else. So as long we are looking on an energy scale of kBT, which is typically around 0.025 electron volt. We want us, in order for it to be a semiconductor and not an insulator, the number of electrons that will move from the valence band to the conductance band should be appreciable. Again, the whole definition of semiconductor is not a hard definition, it's just an estimate. So, you can ask why 2 and not 1. Doesn't matter, it's just a question of definition. So, if we are talking about EG of 4 electron volts, one of the materials that has such gap is diamonds. Well, diamond is even a bit bigger, around 5. So this, for our practical usage, is basically an insulator. Let's estimate with about a quarter of an EV. This is something like silicon or something like that. This is not a great number of electrons at room temperature, but still it's appreciable. Certainly you don't want it as an insulator. So it's traditional to call any material below 2 electron volts of a gap, call it a semiconductor, above it an insulator, although as I said, this is just a very soft type of definition. And the most important property of a semiconductor is that while a metal, as temperature goes up, the conductivity goes down. It's worse for the electric conductance to be at higher temperature. For a semiconductor, it's the other way around. The conductance goes down, but the number of electrons that participate goes up exponentially, so it ends up with gaining conductance as temperature goes up. Now, the usual materials are around the 4 column in chemistry, in the Mendeleev table, silicon, germanium, selenium, tin is even, but a lot of times in industry like 3 and 5 materials from 3 and 5 column, like gallium arsenide or indium selenium, are also used as semiconductors. So what we will do in the next lecture is understand the properties, and the most important properties that we'll try to understand is what installing into the system impurities, what does it do to the system, because I hope all of you know that the main thing about manufacturing semiconductor devices is adding impurities into the semiconductor. And we would like to understand why does it influence the properties of the semiconductor so much. And that we'll do already on Sunday, so let's end here. Not 21, this is just -2. Just estimate of the number of electrons that move above the gap, go into the conductance. The probability of being above the going into the conductance band. Multiply it by 10 to the 20 something and you get an estimate. So this is very low, this is already very substantial. Anything that has a gap that is smaller than 2 electron volts. But as I said, this is a soft definition. In some kinds of usage, diamond, which has a gap of around 5.5 electron volt, is an excellent insulator. But on the other hand, if you put in some kinds of impurities into it, it could resemble the behavior of a semiconductor. So it depends very much on what you do to it. Next lecture, Sunday, usual time, usual place. Next week we'll have at 6 o'clock on Tuesday the second replacement. תודה. בכיף.